All right. So I updated the material repo on GitHub. You can get that through git pull. That might give you some errors because I forgot to consider that you guys would have made changes to your own notebooks. So instead, what you can do is create a new directory and then clone the new version into that directory. The instructions are pinned on Slack general. So once you have the new directory, you should be able to see 3 new notebooks, section 2.1, 2.2, and 2.3. And then we'll be starting with 2.1. So make sure that you have these 3 notebooks first. So in section 1, we started by defining what is machine learning, and then we saw that machine learning models are basically just a box which fits a whole bunch of parameters in order to map input to output. So it makes predictions and tries to improve its predictions based on data you're giving it. Then there's a quick Python exercise. Then we looked at how Sklearn implements machine learning models, and it does that through an interface it calls estimators. Then we we initialized a linear regression model, fit it to a bunch of data, made a bunch of plots, and started to ask the question, how do we evaluate these things? So here we saw the issue of, okay, well, what if not all our features are informative, or what if they're not all good? And without ground truth, how do we evaluate our models? So instead of looking at the parameters directly, so looking at how much we should weigh age versus age squared versus something else, we started to look at, well, we don't care what features are being used. Ultimately, what we care about is how well our model can predict things. I'm going to close that. So if our model can predict well, we don't really care what the model parameters are. We just care that it's doing a good job of the thing we want it to do. And the way that we evaluate that is through some evaluation metric. So in the case of linear regression, we're using R2. And that's basically just a representation of, or a summary of how much variance can be explained by your model. What was this one? Right, this was an exercise in getting R2 and then looking at different metrics. So Sklearn has a whole bunch of different metrics which are accessible through the sklearn.metrics module. And then more importantly, we asked the question, okay, well, what does a metric mean really? We introduced the idea that we don't want, since the machine learning models are intended to fit data as well as they can, it doesn't make as much sense to evaluate the models based on data it's seen, because of course it's going to do well on data it's seen. That's the entire purpose of them. So instead, we showed what the difference was between a training set and a test set. So the training set is the data that you want to use to modify your model parameters. So these are the things that inform your model's decisions. Your test set is data that it has not seen. So if it hasn't seen the data, that data has not affected the parameters. So although the model's job is to fit as well as it can, it hasn't seen that data in order to fit to it. So it's the best. So using a test set is the best demonstration of how well a machine learning model will generalize to unseen data. And since we are always interested in data we haven't seen, that is the entire purpose of building these models. it's the only fair way to evaluate a model. So the second example was a demonstration of features and model complexity. So here, instead of just taking the simple input as x, we took powers of x and then fit those powers to our data. So here we had generated some parabola, and of course it's not defined. So in the first part, we defined some parabola, and then we tried to fit a straight line through it, and then it didn't do so well. And then we tried to fit a parabola, and that fit really well. And then we kept increasing the number of degrees until we were fitting a degree 20, 30, 40, 50 polynomial. And by the end of it, although it followed the curve quite well, it wasn't visually satisfying, because although it was one curve with a nice parabola, even within the curve, you'd see it oscillating, which doesn't make intuitive sense. But those were the parameters which optimized the data that it's seen before. So the model stuck to it. So in the case of overfitting, it's important to consider the number of parameters you have versus the amount of data you have. And one way to evaluate that is by something we're going to see today, which is cross-validation. So are there any questions on that material so far? Let me go find where I put the Q&A. No questions.
Next, there is a question from Stephanie that is trying to maybe relate that to study, or maybe have a little bit of an example of an actual study, like put it in context of some scientific question, maybe.
Continues here. Is it possible using an example study? I was getting kind of lost yesterday in what we were doing exactly. Okay. So I think the first example in today's notebook is predicting diabetes. Let me check. Right. So based on what we saw yesterday, if you had a bunch of patients come in and then you took things like their blood pressure, their cholesterol, you measured how tall they were, how much they weighed, those would be your features. And then if you're trying to predict something of interest, for example, are they at risk of a heart attack, or will they have a heart attack in the next X number of years? Well, so you can take those four features and then make some predictive model, and then those features are probably not going to be enough. But if you were to then increase the number of features, so you add in information like age and age squared, and then you add in things like weight, and then you take a power of that and you put weight squared. Now you're adding a whole bunch of features to your data, not necessarily adding information, but you are increasing your model's ability to use, you're giving additional functions that your model can use to fit. So age and age squared may or may not predict well. Oh, sorry, age alone may or may not predict well, but age and age squared is certainly going to predict, it certainly has the ability to predict better, if only because it can find more complicated functions. I don't know if that answers the question. Okay, good. There are questions. So one of the questions was the difference between input data and labels. And that is a very important question. It is very important to understand what the difference is. So here, the input data is the data that you're using to make predictions. So if you're looking at the heart attack example just now, it'd be cholesterol. That's your input data. The label is things that we are trying to predict. So cholesterol would be the feature, and then the thing that we want to predict is heart attack. So conceptually, how do the number of parameters relate to the number of variables? So it'll kind of depend on the model that you're using. In linear regression, the number of features, the number of parameters that you have is equal to the number of features, since you have one weight for one feature. Right. And then there's two questions which are very similar, which is why would we square age? So there are some neurodegenerative diseases where things accelerate with age. So you're not going to see any difference when somebody's very young, and then you're going to see a small difference when they're a little older, and then much larger difference as they get older. So that accelerating is kind of mapped by age squared. The reason I keep using it as an example is age and age squared tends to be very common examples in neuroscience regression models.
And possibly you could go to edge, to the power of 3. It's just like a,
Oh yeah, exactly.
It's just that we don't know the exact relation between edge and the variable, and therefore we could model that more or less with a linear thing, which is just edge, linear plus quadratic, edge plus edge square, or some combination of edge and edge square, and so on and so on. And that's where model complexity is kicking in.
And then one more, which is if our feature is not like age and weight, which are nominal, so they have real values, and if they're instead binomial variables. If instead you had a categorical 0, 1, could we still use linear regression? Pretty sure you could. That's just going to give, so because you don't have much resolution in the number in your input, your linear regression is basically just going to be a weighted 0, 1. So if it's the only variable you have, you're not really going to be able to have much expressive power. But if you have other variables, then that certainly could be included. Okay, so I'm going to move on. So yesterday we had some exercises. We didn't really get many questions about this. So I don't know how many people actually did it. But here, so the point of question 1 was to make you compare multiple models. So not just the simple linear regression one, but also look at how decision trees behave and how support vector regression works. And then one of the questions that I hear a lot is things like, oh, well, could we use support vector machines for this or that? And the answer in basically all of machine learning is one of two answers. The first one is it depends, which is super unsatisfying. And then the second answer is cross-validation. So if you want to answer basically any machine learning question, it's going to be one of those two. So for cross-validation, we can use that to perform models not just in different, not only for different data splits, but also for different models. So linear regression, for example, looks very different than support vector regression, but you can still directly compare them using some metric. The second question was about fitting data which looks a little bit more complicated than the straight lines that we saw. So there, that was, instead of having some weighted line of a couple different parameters, we have a varying sinusoid. So if you were to use just a line to fit a sinusoid, you'd end up with the mean, and in this case, it would just be a mean of 0. So fitting a line, some function with 0, is kind of not very satisfying. So one of the things you could do was take the polynomial powers that we had just talked about, and then improve the fit of the sinusoid. Now, depending on which parameters that you use for each one of the different models, you'll get different results. Right, and then Q1.3 was just trying to improve your performance using the polynomial features. Okay. So there's a bunch of questions about the solutions. We could provide the solutions. There weren't any solutions. Yeah, so I don't have the solutions, but I can write something up after the workshop. So they're not going to be available this afternoon, but they'll be available sometime over the weekend. Okay. Some of the lower hands. Okay, and then one last question, which comes up a lot, which will we be talking about how to choose which type of model to use? And yes, because we do that through cross-validation. All right, so in this second section, we build off the contents and the information that we got from the first section. So we saw a test set, we saw different models. In this section, we're going to introduce what cross-validation is, how a couple different evaluation metrics, and then demonstrate some useful visualizations so you can better understand your model performance. So here's some easy definitions. So we've already seen the training set and we've already seen the test set, and we've kind of mentioned the validation set. So as I mentioned previously, the training set is the data which directly informs the model parameters, and the test set is what we use to evaluate model performance. So one of the things I said partway through it is that as soon as we use the test set, we need to stop all evaluation and we need to stop training the model, and nothing else can change. Using the test set is the last thing you want to be doing right before you put the numbers into the paper and then you send that off. So, I mean, realistically, that's not really how that goes, but conceptually, that's what it should be. So we basically intentionally broke one of the cardinal rules just to demonstrate why that's kind of an issue. So if we select a model based on the results that we got on a test set, we're not directly affecting our model parameters, but we are implicitly informing them. And what I mean by that is that if you were to randomly initialize your linear regression, and you did it for, I don't know, 100 or 1,000 different models, some of the randomly initialized ones are going to work better than others. So if you picked one of the ones that worked best, so the model wouldn't have seen any of the data, but because you have selected it based on performance results, you are saying that, yes, these parameters are good. So although there isn't a direct observation of data, there is an indirect one. So how can we tell if our model is doing well if we can't evaluate it? Well, the answer is, as we did before, we'll just split up our data set again. So the idea of cross-validation is that we'll have 3 test sets. First, we start with a full data set. We split it into training, validation, and test. The test set we just take and we set aside. We'll use it at the very end. Now, within the remaining set, we want to split that again. And then we're going to use one to directly inform our parameters, and then the other one to evaluate the model performance. So when we do cross-validation, we don't necessarily have a fixed set for validation, because that would just give us a evaluation of one, or evaluation data set of one, which means that we wouldn't be able to get a distribution, and we could suffer from bad luck. So for example, if our validation set is exceptionally easy, then we can say that, okay, well, I will select the model that does really well based on a very easy data set. But if we vary the actual validation set, and then we take different parts of the training set, then we can have we can be a bit resistant to that, and then not have to worry about our validation set happening to be easy by chance. One of the other nice things is that by having multiple splits, we can also get a distribution for model performance. So there, it's not just the one number for evaluating, it's an entire distribution. So normally they'll be somewhat symmetric around some mean, but other times, depending on parameters, you can get very bad ones and very poor ones. And knowing what that distribution is will give you an indication of how well you can expect it to behave in the generalized data. So one of the ways that we can do cross-validation, and there are many ways, but one of the more common ones is k-fold cross-validation. So in k-fold cross-validation, what you do is that you take your training set, and then you split it into k different sections. So here we show 5-fold cross-validation. So in the first set, we take 1/5 of data, we set it aside for validation, and then we train on the remaining 4/5. In the second fold, we take a different slice of the data, we take that aside, we train on the remaining 4/5, and then evaluate on the 1/5 again. And then you do that for every possible split. So in this way, we train on the entire data set, and then we validate on the entire data set. But we're never doing both at the same time. So we're not training on one data set and then evaluating on that same data. Now, the question that basically always comes up, and Yarkoni mentioned this briefly yesterday, is how do we select K? And this is one of the few answers where cross-validation and it depends doesn't really fit. So typically you'll want a value between 5 and 10. Whether or not there's like an optimal number for it kind of doesn't really matter. The idea is that you want to have enough data in your validation set in order to account for the variation in your data. So if you have very large K, for example, so K of 1,000, well, you're going to be training on most of your data and then evaluating on very small amounts of your data. And then as you change the amount that you're, as you go from one fold to the other, you're going to have some very similar models because the data is not the training data is not changing very much from one fold to the next. So not only are you going to have some noisy results, which can be compensated for by the number, but the models are not really changing, so it's not as informative as it could be. So anywhere between 5 and 10, you're fine. So there's a question here about K depending on sample size, and yes, that does relate to accounting for the variance in your data set. So you want enough in your training set so that you can learn what the variance is and account for it, and you want enough in your validation set in order to measure it. There's also some questions about performance, but 5 and 10 is basically you train 5 models and then you evaluate it. So that's not too heavy. Okay. So we're going to do an exercise in using k-fold cross-validation. But this is where it's not strictly necessary, but extremely helpful to understand some more advanced Python concepts. So one of the, I don't think this was covered in Monday's session, but in a lot of different programming languages we have something called objects. And although we haven't seen what objects are, we have used them. So for example, our models previously were objects, as was the polynomial features class that we used. So conceptually, an object is very similar to a variable. So if you have some variable, it stores some data. So the example I have there is if you have A, it doesn't make sense alone. But it does make sense if you have A is equal to 5, because now that A points to the data 5. And objects do the same thing. The major difference is that objects can also have methods stored along with them. So they can have different types of data along with methods. And methods are basically just functions that use the object's data. So if you're not sure what that means, that's fine. There's enough examples there that you can just copy paste how to use them. And for 90% of the stuff you're going to see, that should suffice. But if you're looking for an understanding of like how the different parts of Sklearn or Python code might work, one of the things to keep in mind is that objects are a thing and they are commonly used in Python. In fact, literally everything in Python is an object. But we'll set that aside. So the reason I bring that up is that there's a special type of object in Python called a generator, which returns values when you put it in a for loop. So k-fold is something which is a generator. So here, if we look at the code, we import the modules that we want. Here, this is where we define the object. So kf is equal to k-fold. So now kf is an object. When we do kf.split, this creates a generator, and then we can have this kind of structure. So for the train index, valid index in our generator, we can do a bunch of things. So if we just run this cell, so our X data is the numbers from 20 to 30. Our Y data is 40 to 50. Here what we said is that we wanted twofold cross-validation. So what that does is that it splits our training data into the first half and then our validation data into the other. So if we treat X as our training data, we see that the first split for the training data is 25 to 30, so the last half of this. And then the train label, or the Y, is the corresponding values in the second data set. Okay, so we're going to see a practical example of k-fold cross-validation, and we're going to use Sklearn's one of the Sklearn's sample data sets instead of our previous polynomials. So previously we'd used some toy examples, mostly to generate data that we knew how to verify the answers directly. Sklearn provides a whole bunch of data sets which are labeled, which are relatively simple, but that are still not ideal. Ideal in the sense that they're not toy simple functions. And one of them is low diabetes. Or one of them is diabetes, the diabetes data set, which we can access through low diabetes. So as always, we can use the help function, and that'll print out information about this. So just for the time being, there's a whole bunch of information on what the actual data is. I think if we do description, right? And then here we'll see a more detailed description of what all the different features are. But for the time being, we can just treat it as we did before, where we have our X input and then our Y output labels. And then we can get the data using this command. So sklearn.datasets.loadDiabetes. And then just so that we can see what's happening, we can take a look at the shape. So dot shape is a property which is present across all NumPy arrays. And then D labeled similarly. So what this says, so if you remember from yesterday, the convention is to use the number of samples in the first dimension. So 442 here. That means the number of patients that are in the data set. And then the second dimension is the number of features. So if we look at the description here, we see the different features out here. So age, sex, BMI, blood pressure, and I'm not a doctor, so I'm not quite sure what the rest are. But they are apparently related to diabetes. So we'll just hide this. And then lastly, we're going to split our data set into our training and test sets. So this is just the part where we want our where we want to keep our test set, which we're going to use later for evaluating the model. All right, so this is the part where people can actually start coding. So here are the instructions for this exercise. So first, you'll want to create a KF object with 5 splits. Then you'll want to put that KF object into a loop and then split the data and the labels so that you can use the piece of code that I demonstrated earlier. So you can just copy and paste that. In each iteration of the loop, initialize and train a new model. Save the R2 score for each trained model. So you'll notice here that there's R2's score list, which just initializes a list. Then we'll print out the average score across all the different trained models, and then we're going to plot the scores. All right, so I'll give you a few minutes to do that, and then once you've completed this part, raise your hands that we know what the general progress is. If you have any questions, put them in the Q&A. We'll try to help you out.
Lex, there's always a bit of confusion whether people should be using Q&A or Slack. What do you recommend?
Well, so if they want, sorry, I'm not going to see so I've got too many windows open. So if I can't monitor Slack on top of everything else, the Q&A is much easier for us to monitor and then address directly. If you're looking for issues using Jupyter, so for example, if you get some error that you can't figure out, it's a lot easier to go back and forth on Slack. So if it's just a question that you're looking for clarification, that's not going to require back and forth, then Q&A is better. If we're going to need additional information or something, then Slack is better.
Okay, so for
as the default, the Q&A is probably better.
Okay. So basically simple direct question on the what's something like please put it in Q&A, and if you think that's something that we'll have a conversation going on, put it on Slack, and some of us will be monitoring the Slack while Lex, you can monitor or you can see what's going on in the Q&A.
Yeah.
Jerome is saying that the question about spreading subjects across folds is important. Maybe you want to answer that one, or maybe Jerome, you can unmute yourself and answer this one.
Yeah, sure. So Maya was asking if it's better to split the data by participants, or is it okay to have data from one participant scattered across k folds? So if and usually it's the case that you want to know if your model will work on a new participant, so generalized to a subject that hasn't been seen at all. So in this case, it's crucial not to spread the data from one participant across k-fold. So you want to leave whole subjects out in the test set that don't have any data at all in the train set. And the scikit-learn cross-validator utilities have usually a parameter called groups, where you can specify a variable by which the data should be grouped so that a group isn't spread across the train and test set.
Yeah. So I think the train test set has the stratification, or it's like stratified something or other.
I think stratification is what they call stratification is something else. It's to make sure you have the same proportion of each class in the training test set. It's only important when you have smaller data set.
So this question here, should we calculate score for trained data in the loop or for valid data? That's a good question. So if you do if you report the training score, so if you report the training score is based on evaluating your model on the data that you've already seen. So yes, you can report it, but it is not an indication of how well your model is doing. What is going to be informative is if you compare the training score to the validation score. So the answer is you can do both and then compare the two, but only the validation score should be used for model selection. One of the things that is particularly useful when you do actually get both is if you see that your training data, your training score is very high and then your validation score is very low, that'll tell you, or that'll give you a hint about changing your model so that you have either fewer parameters or simpler data. Right, one of the questions is initializing a list. So this part here, this is initializing a list. Initializing is basically just running the function that just starts it. So before we run this line, for example, our toScore list is not defined. So Python doesn't know if it's a variable, if it's a list, if it's a string. Here, what we're doing is we're basically saying, okay, this is a list. It's an empty list, but it's still a list. Then what that lets us do later on down here is append. All right, so somebody reached R2 of 0.43 and 0.5, and yeah, that's roughly what you should be getting. All right, so I'm going to move on to solution, and I'm going to be super sneaky and then just put in my code. So here, the first thing that we do is create the kf object. So here we do kf is equal to kfold with n splits is equal to 5, because that was the instruction. So if you did n splits of 10, whatever else, it's fine. Then we'll just initialize the list, and then we're going to go through a loop. This I don't think we actually use. So the structure that we said before was we put in our data, our labels, and then we get a whole bunch of indices. And we can get our train data, and we can get our training labels, and then our validation data. Then we initialize our model, we fit it to our data, and then we get the score. So what this does is that it looks at our toScore list, which is the list that we initialized up here. And then it calls the method append, which is just going to add a value to the end of the list. And then we just compute the score on the validation data. So one of the things that would be useful would also get it for the train data, but we're just looking at to see what the validation data is, the validation score is for this example. And then there's a bunch of code to plot it. So when we run this cell, what this gives us is a distribution for our score across the different folds. So depending on so if we had randomly selected our validation set from our total data, we would have gotten a score of either 0.47 or 0.48 or 0.57. So some of these can be like significantly different. So knowing what the distribution is kind of helpful. So if you'd gotten bad luck and then gotten on the 0.37, you say, okay, well, this model isn't so good. But here, the general distribution is that you can say that, well, the mean R2 is 0.5 and not the 0.37 you might have reported. So note that there is variation between each fold. Right, so this is the part I was just saying, where you might get if you were only to use a single validation set, you're not going to get the distribution. Now, if you found this a little tedious, Square agrees with you. That was largely an exercise in Python. So I apologize to the people who had too much trouble with this. Sklearn is typically a lot easier to use than that. So the intention there was part Python exercise, but also just to walk you through conceptually what it is that cross-validation is doing. So you select the model, you select your subset of data, you fit your model, you get the score, then you start again. So so the solutions to everything are in the solutions directory. So if you want to copy paste it from there, that's also fine.
There's one person asking, Lex, if you could scroll again and...
Right, so the solutions and everything I just posted is there's too much to copy and paste from the screen. So if you open the solutions document, the solution directory, all of this code is there. So TDM aside, if you find yourself doing something over and over again, which is tedious in Sklearn, there's very likely some kind of helper function which is going to make your life easier. And one such example is the cross-val score, which does exactly what we just described. So if we look at the documentation using the help function, we can see what it expects as input. So this is the part where knowing what an object is kind of important. So here our models, after we initialize them, are objects. And then we don't pass in the fitted or anything, we just pass in that object. And then it'll take your data and then your labels, and it's going to do exactly what we just did. So by default, it goes to k-fold cross-validation, and it's going to return a list of scores. So instead of what we just did, let's do something a little different where we leverage Sklearn's tools to our advantage. So here what we want to do is we want to get our data, get our model. We'll want to save the R2 score for each trained model and then print out the average score. And then as we did before, plot it. So I'll give you guys 2 minutes to fill in the blanks here. So here, cross val score is accessible because we imported it here. Then you can take of parameters you're supposed to use. Yeah, and then once you're done and this part can generate a plot, raise your hand on Zoom. So the question is, why use the mean score across folds? If a fold is much better than the rest, it would increase the mean score overall. Sort of. So the question of, so it's not entirely clear whether your model is doing well in one fold because it actually learned anything better, which is inherent to the data, or if it just got lucky. So the reason that we're doing cross-validation is so that we can get some distribution of what we can expect on seeing data. So we'll basically want to take the entire data set. So before we actually want to generalize before we want to put the model out to the world, we'll want to use our entire training set without validation and then evaluate on the test set and then use that value to say, okay, this is the model, this is how well the model is going to be doing. And so yeah, what I was talking about for the distribution is the mean is just a convenient number, because there we can directly compare one number to the other and then look at the distribution, look at the difference. But if you look at the previous plot here, the mean will tell you the average. But if what you're interested is certainty, for example, you might be more interested in a model which consistently gives you 0.4 rather than a model which might give you 0.6 versus 0.3. Where was I? Okay, so show of hands if you're able to get this to generate the plot. Good, good, good. So many hands are going up. Right, so Jerome points out that one thing to keep in mind is that the folds are not independent, so they do have overlapping data. Okay, let me go find where I put the data.
Yeah, what I meant by that is that even though we get several scores and we can plot their distribution and look at their standard deviation and so on, we have to remember that they're not independent samples, so we can't use them to, for example, assess statistical significance of the
right. Okay, so basically initializing the model is the same as we did before, and then scoreless is just cross-val score, model, d-data train, so on. Here, if you looked at the documentation of a cross-val score, there is a CV variable, which takes in different types of data. If you set it to an integer, it'll just do k-fold cross-validation with that many folds. So if we run this, so instead of having like the complicated for loop with this generator and the split function and all that, we can just very easily just call the one function and get the same plot as we did before. So I guess I'm kind of advertising Slurn a bit, but it is a fantastic tool to make your life a lot easier if you're doing machine learning. So one of the things that you might notice is that even though it's the same data set, some of these results are not the same as the ones that we saw previously up here. And the reason for that was pointed out yesterday, where train test split actually randomizes the samples. So this is a different split than we did in the previous exercise. So if you're seeing a difference, it's completely normal. So there were a few questions yesterday about different types of cross-validation methods. And I have intentionally left these all commented out. So don't run them just yet, or don't uncomment and then run them. So there are other types of cross-validation, and one of them would be leave P out cross-validation. In the extreme case, we have leave one out cross-validation, where we train on all samples but one, and then validate on that, and then do that for every sample. So that generates a lot of different models, or a lot of models, and validates on just the one sample. So you don't have as much predictive power in the one validation set, but you do have a huge distribution of them. The main issue with leave P-out cross-validation is that the computational complexity, so how long it takes to actually compute, increases combinatorially, so a factorial basically. So you tend to not really want to do it. So I've got a reasonably powerful desktop, and this takes several minutes to run, even though it's a very simple, it's a relatively simple data set, which is small and a relatively simple model. So in practice, leave P-out is there, but you're probably not going to use it. If instead you're looking for something with behavior which is similar to leave P-out, but then without having to worry about the huge computational complexity, you can use something like shuffle split, where it's probably closer conceptually to, well, it's somewhere in between leave P-out and K-fold cross-validation, where instead of taking fixed and then independent validation sets, you're just taking some random subset. So our cross-validation has been used mostly to evaluate our models, but we can do something a bit more than just evaluate them. So the parent module for a lot of the cross-validation methods, which is called model selection, kind of hints at that. And one of the reasons for splitting the data set between training, validation, and testing is just to avoid informing our models. So one of the things that we saw in yesterday's exercises was that we can perform cross-validation across more than just parameter values. So you don't necessarily need to have linear model. You don't necessarily have to be comparing linear regression to just linear regression. A lot of cases you might ask, okay, well, I want to use an SVM or some other model. Or if your PI says, I want to use this newfangled shiny thing I just read in the paper, then you might want to compare that to what you're currently using and then say, okay, well, yes, this does work better with our data versus it doesn't. So cross-validation shouldn't be just used as a sanity check for a single type of model. You can also compare results across models. And that's probably where, and that's why when people ask, oh, well, when should I use this type of model or that type of model? You're often not going to get a straight answer, because the answer is, it depends, use cross-validation, whichever one scores the best is the one you should be using. So that's the unsatisfying answer, but also one which is a bit more empirically sound. So just to wrap up cross-validation, so at its core, cross-validation is just about making sure that we evaluate our models fairly and that the things that we report are accurate. So if we have a fair comparison, we can empirically evaluate our models without having to worry about not only random chance, but also our own biases affecting choices. So personally, I don't like decision trees. If somebody tells me a decision tree does well or a random forest does well, I tend to not believe them and then use a different model anyway. But even if I don't like them, I will still test them and then compare them. And then I can say, well, it's not just because I don't like them, it's because my results say that they don't really work with our data. Okay, so that's kind of the gist of cross-validation. So if there are any questions, please put them in the Q&A. We'll take a few minutes for that. Why do we generally control the splitting while using train test split, isn't it better when it's totally random? I'm not sure what you mean. So the train test split does randomize the data set. So when we say train size is equal to 0.6 or 0.8, we're just saying that is the proportion that we want. This question of, I was under the impression that leave one out cross-validation was the norm in machine learning. Okay, question just disappeared. Am I wrong? Apart from taking longer to run, does it present advantages compared to the k-fold method? So Jerome points out that it used to be a lot more popular. K-fold, I think, is much more in vogue. I'm not quite sure about the reasons for that, but if nothing else, the models train much more quickly. So you have to train fewer models using k-fold. So that alone is kind of an advantage.
One of the reasons is that there are two sources of variance in the errors. There's the variance that's due to the different test samples, and also the variance due to the different models that have been trained on different training sets. And when you leave one out, all the models are basically the same, trained on the whole data set.
Right.
There's only 1 point changes. And when you use, for example, k-fold, of course, the training set overlaps, so they are not really independent, but still you get a bit of variability in the training sets. So you get a few different models.
And just to reinforce that, that's why you should try to avoid leave one out in most cases.
The question about the random state. So random state, what that does is it just fixes the random seed. The question was, while writing ML code, a lot of people use random state is equal to 42 in train test split. So the actual number doesn't really matter. Train tests, the random state is just to say, we want to make sure that whoever runs this code gets the same results. So one of the things that I'm intentionally doing here is I kind of want to highlight the fact that you're going to end up with some messy and random results in your own data. So if you see something that changes from one step to the next, that's not unusual. That is expected, and you're going to see that a lot in your own data. In terms of presentation and trying to explain a certain concept, you don't want users who are new to something come up with something which is completely different and then doesn't illustrate the point you're trying to make. So by some random chance, these could have been all identical scores, at which point me saying, okay, well, sometimes you get different scores would kind of be undercut by that. So the question of random seed is equal to 42 specifically, I'm guessing the 42 is just Hitchhiker's Guide reference. I don't think there's any other meaning to it. So the random state is more about presentation and illustration than actually something statistical. So if you used k-fold and the average is good, do you then run the model on the whole data set before moving to the test set, or should you extract the k-fold model that did the best? So there was a question similar to that previously, and you want to be training on the entire data set and then evaluating on the test set. Okay, so there's a question, can we hear more about stratified k-fold? See, that's one of the ones I'm a lot less familiar with. from square dot model selection. Right. So one of the things that you'll probably run into is if you have different types of groups in your data set where they're not really a variable of interest, but you kind of want to make sure to not be biased or influenced by a random distribution of them. So for example, if you have some subset of your data that likes to wear top hats versus people who prefer bowler hats, you don't want to be training on only the people that like top hats and then evaluating on the bowler hats. If it's not a variable which is going to confuse your model and it doesn't matter to the label, then it doesn't really matter. But as a precaution, you want to make sure that you'll have a representative set in your training set. So what we mean by representation is in order for your models to generalize well, it needs to have seen data from that it's likely to see in the test set. So not the exact same data points, but you want to make sure that if you've got top hats in your training set, you don't want it to be suddenly very surprised by bowler hats in the test set because it's never seen them before. So if the proportion is something like 40% of people like bowler hats versus 60% for top hats, you want to keep that kind of proportion the same. So what stratified k-folds does is it makes sure to preserves that across the different classes.
I think it preserves exactly the proportion of the classes themselves, right? It makes sure, for example, if you're classifying patients versus controls,
yeah,
you get always the same proportion of patients and controls in each of the folds.
Okay. So there, if you're just trying to predict whether a hat is top hat versus bowler hat. Okay. Okay. There's a couple questions about statistical tests to compare models. That is also where my math fails me. So I know that you can use something like a permutation test, for example, and that what that does is it will shuffle the labels in your data set. The idea being is that if you can fit your data to random, not associated data set, then you're probably not really learning something about the relation between the two. But if you're able to predict much better on the correctly labeled data set than you are on some random shuffling of them, that should tell you that you're actually learning something significant. So I think that other than the permutation test, there must be some other things that we can compare models directly, but I'm not sure.
The permutation test can help you, as you said, rigorously test if the score you get is different from what you would get if there was no signal. But with cross-validation score, you cannot do a statistical test to compare different models because, as we said, the scores that you get from the k-fold, the k-scores you get are not independent. So in order to compare models rigorously, you would have to, for example, train them on one data set and then test them on another data set or on different data sets, or train and test on several completely separate data sets and compare these scores.
Right. Permutation testing would only test against chance. Yeah, so that determines significance. We're going to move on to the next section, which is section 2.2. regression versus classification. So if you open the directory, you'll see section 2.1, which we just completed, and then section 2.2 for regression versus classification. So just open the second notebook, and you should be able to see this. All right. So in the previous section, we mostly used data which was best suited for linear regression models. So our labels were real valued. A value of 4 was, so we knew that a value of 4 meant that it was more than 3.3, but less than 4.5. So if our model had a prediction of 3.9, we knew that it was a better prediction than if it had predicted 2.9. The reason is that just 3.9 is closer to 4 than 2.9. So there was an ordering to the numbers, and that type of problem is a regression problem. The other type of problem, which is very common, is classification. So there we have some group of data, and then we want to, some amount of data, and then we want to assign a particular group to it. So we want to classify it. So for example, in medical applications, one of the things that you'll want to do is produce a diagnosis. Does this patient have Alzheimer's? Are they showing signs of dementia? Or if you're looking at an image, you might want to do tissue segmentation, where you take a look at the image and then you say, this is or is not gray matter, or this is or is not a tumor. So a classifier is a model that produces a categorical label for input samples. So a variable whose values corresponds to different classes or categories is a categorical variable. So what that means is, so if we're looking at tissue segmentation, so in the brain we'll have white matter, gray matter, and CSF, cerebrospinal fluid. So one of the common segmentation tasks is to assign a group to each one of them. So for white matter, you might say, okay, well, this is group 0. And then for gray matter, you'll say that, sorry, for the other matter, you'll say group 1. And then for CSF, you'll say group 2. So in this section, we're going to see at how classifiers behave, how to train them, and look at some of the data which is best suited for classification instead of regression. Now, the first classifier that we're going to look at is, it has an unfortunate name and it trips up a lot of people that are beginning in this. And the classifier that we're going to start with is logistic regression. So the reason it's called that is buried in the math, but despite its name, it is a classifier and not regression. So we're going to follow the same steps as we did for the regression examples previously, where we're going to load a data set, we're going to train our classifier on it, and then we're going to evaluate it. So the data set that we used in the previous notebook was the diabetes data set, which they're not predicting yes/no diabetes, but rather an indicator of the progression of diabetes. So there are a number of other data sets, such as the iris data set, which I think is very commonly used specifically for what we're doing, which is illustrating classification. And it has 4 features, which is the sepal length, sepal width, width, and petal length. And then based on just those 4 features, the goal is to say what type of iris it is. So we're basically just looking at flowers and then predicting which flower it is. So we're going to do very similar steps where we're going to load the data set. We're going to try to visualize the data set. Oops. design issues. We're going to try to visualize the data set. Then we're going to initialize the logistic regression classifier, also known as logit. We're going to do fivefold cross-validation. We're going to print the mean performance and then plot the distribution. So the parts which are going to be relatively new are just loading the Irish data set, but it's the same as we did with load diabetes. And then trying to visualize the data set. So before we can get started, we should examine what is the shape of our data. So when we load this, what are our data dimensions? So if we load our data, we just run this cell. We'll see nothing happens, as it shouldn't. Let's put this down here. So if we want to print out the shape of the data, we just have to do print Irish data.shape. Then here it tells us that we have 150 samples. So whoever collected the data set looked at 150 flowers and then measured 4 things about them. Now, if we wanted to plot this, we wouldn't really be able to, because here we're looking at a 4-dimensional, we're looking at points in 4 dimensions. So instead, what we can do is plot one feature versus another. So we looked at how to index arrays yesterday. So instead of looking at 0 and 1, try to plot 1 versus 2 or 3 versus 0 or something. So I'll give you guys a few minutes for this part. So one of the very simple ways to do that would just be plot this directly. But then you can't really tell what belongs to which class. So we're going to see how to simplify that a bit later on. So there's a question of, is there a way to know directly which features are the most interesting to plot without trying all the combinations? Not a priori, no. But so there, it's more for you to be able to see like try to visualize what it might look like in 4 dimensions. So you're not really going to get a clear picture, but if you were able to, so we can see that like there seems to be a cluster up here, right? And that seems to be separated from this other mess. So it looks like when we look at the first two features, for example, it might separate one of the clusters. And then if instead we did 0 and 3, well, we see that there's another cluster over here. Now, because this is in 4 dimensions, I'm like 60, 70% sure that this is the same cluster as previously. But you can at least take a look to get a sense of what your data looks like. And just as a side note, if anybody is feeling so incredibly lost that they're not sure what questions to ask, please either follow along in the solutions just to catch up, or ask us questions in Slack. There, one of us will be able to get get onto Slack and then address and hopefully get you to catch up a bit. So there's one question which uses something called logical indexing, and although that is correct, we're not going to take a look at that just now, though. That is what we're going to use later. So there's a question about what return XY does. So if we don't have return XY, we don't end up with this structure. So right now, the thing we're interested in is that we want our input data in one variable and we want our labels in another variable. If we were to do, just call it dat, datasets.load iris. So move this over to the cell below. So if we were to do something just like this, this works just fine. But then what you're left with is a dictionary instead of two variables. And I was kind of avoiding the, I was trying to avoid the use of dictionaries. So this is mostly just to simplify how we're working with the data. Okay, and then getting the number of unique labels. You can use NumPy. NumPy has a unique function which just takes in data and then returns the unique values. Oops. So here we see the output, which is 0, 1, 2, which tells us that we have 3 classes. Yeah. Okay. So the thing about the dictionaries, if you're confused about it, that is exactly why I was trying to avoid it. So don't worry about it. Okay. So we're just going to look at the solution. So here we just load the data, we'll split it, we initialize our regression. So lib linear here is not strictly necessary, it just works better with smaller data sets. So it's not going to throw an error like the default solver does. And then we get our score list, and then we print what we were asking for. So this is just the cross-validation scores across the 5 folds. So now looking at the results, we have 2 questions we should be asking. What score is being plotted? So previously what we'd done is used a linear regression, and then we got the score from that. And that returned the R2 score. Now, R2 makes sense for regression problems because it's looking directly at like the differences between the samples and the predictions. Here, R2 doesn't quite really make sense because here we're just trying to predict labels, so groups of 0, 1, 2. And it's not entirely clear if there's a big difference between 0 and 2 versus 0 and 1. So in order to know what is actually being plotted, we'd have to take a look at the documentation. And if you're ever using any kind of function, it's super important to look at the documentation. And then if we were to look at the documentation, we'd see that the score which is being returned is the mean accuracy. So this plot is the mean accuracy on the validation set of each of those folds. Now, the follow-up question is this plot informative? So just a show of hands, who thinks that this plot is informative? I should always ask the negative questions. Who thinks this plot is not informative? All right, well, I got 5 responses. I'm quite happy with that. So the answer is it's kind of informative, which is kind of cruel on my part. So this does tell us the accuracy across the different folds, and that part is fine. The issue is that accuracy is not always the best metric. So it is a good summary metric, but if you don't know what the data is to begin with, accuracy may not make sense. So for example, are the classes equally difficult to predict? So where is the error coming from? Are you confusing class 0 for class 2 or class 0 for class 1? And that kind of information will tell you what steps you need to do in order to correct it. So for example, if your model has a whole bunch of trouble distinguishing between your 2 classes of interest. So for example, if you have 3 classes of patients, you have healthy patients, those with mild cognitive impairment, MCI, or outright Alzheimer's. So those would be your 3 classes, Alzheimer's, MCI, or healthy. Now, if your model can't tell the difference between your 2 classes of interest, which are probably MCI and Alzheimer's, you're not going to have, the model is not going to be useful, even though it could be super accurate. So one of the ways that we can actually visualize that and then just get an intuitive understanding of where the model is failing is something called the confusion matrix. So if you have a problem with C classes, so in the previous example, we had 3 cases, healthy, 3 classes, healthy, MCI, and Alzheimer's. So the confusion matrix would be a 3 by 3 matrix, and it functions a lot like a bar plot. So for each sample, it looks at the point, prediction label, and then adds it to a bin in the confusion matrix. Correct predictions along the diagonal, where prediction is equal to the label, are good. Anything which is off diagonal is a mistake. It's going to be a lot easier to understand what this means once we see the picture. So the first thing is, so not surprisingly, Sclaren has a thing to create confusion matrices. So the first thing to do is look at the documentation. What input is that function expecting? Then what we're going to do is create the logistic regression model. We're going to fit it again. We're going to predict, and then use the predictions. These steps are not as important if you just use the plot function directly. So if you wanted to go through the steps and then get the confusion matrix, then you would do something like this. But because Sclerin is so friendly, what we can do is get plot confusion matrix directly. So here we import our the function that we're looking for. We initialize our data, and then we train our data, or we train our model on our data. And then we can take a look at the plot confusion matrix documentation and see that it expects 3 things, minimally. There's a whole bunch of other options, but these are the important ones. So we need to supply our estimator, our data, and our labels. So I'll give you a minute to get the confusion matrix from the data and the labels that we have.
And meanwhile, Lex, there's a couple of questions in the chat. I don't know if you've seen that. There's at least one.
The chat is moving way too quickly for me to notice. What was the question?
I do not understand why the previous figure is informative. Accuracy for each feature or class would be informative, but not that plot goes across different validation groups. So maybe a little bit more explanation on that plot.
Well, so this plot just tells us how accurate our model is across the different folds. So this is model evaluation. So the question is the plot informative? And it is informative because it tells us our score, which is the mean accuracy, is fairly good. But without additional information, accuracy is not usually sufficient. So here, if we have reason to believe that the accuracy is a good measure, then yes, it's informative. But there's a whole bunch of other information that we can't get from accuracy. So the reason that we're doing the confusion matrix, for example, is that we can't see where the errors are coming from. So accuracy is a good measure if you just want to look at the one number. But if you're looking for sources of error, for example, you're not going to be able to tell. So for these, for example, I don't know if it's confusing class 0 for class 1 or class 2 versus it's just having problems with all the different classes.
Yes, and I guess the simple example is that if you have so accuracy is the number of properly classified.
I'm going to cut you off there. We see that in great detail afterwards.
Okay, thank you.
Yeah, arguably even painful detail. No, Jerome's spoiling my entire thing.
It's absolutely fine to have repetition.
No, I know. Repetition is good.
It's a good thing if you have repetition of the same things. Don't worry.
Yeah. So one of the things from, anyway. So what Jerome is posting in this Slack is really good information, and we're going to see examples of that later down in the notebook. Okay. Now we're going to look at the actual plot of the confusion matrix, which is just one line, but it's important to read through the documentation to understand what it's actually doing. So when we plot this, we'll see a 3x3 matrix. So on the x-axis, we see the predicted labels. So this is what our model is saying. And on the y-axis is the true label. So that is what our data says is the label. So here on the diagonal, this is where there are correct predictions. So here we saw that we made 17 predictions for 0, and there were 17 that were actually 0. Then here, if we look at the off-diagonal terms, we see that there were no errors, so we didn't confuse one for the other. So our model classifies class 0 very well. And then here on the in the center of the matrix, we see, so we predicted class 1 21 times, and then it was true 21 times. But there were 2 samples in our data set that were actually labeled 1, where we said that they were actually 2. And then we got all our predictions for this one correct. No, I got that backwards. Predicted label 2, true label. Okay, so yeah, we predicted that it was 2 when it was actually 1. I hate these plots. I always confuse the 2 axes. So here we can see, depending on how much data you split versus what you evaluate on, you'll see a difference. You'll see something different, but generally the error is going to be between classes 1 and 2. So the confusion matrix is a bit more informative than the accuracy plot, mostly because here we can see where the errors are coming from. So we see that the last 2 categories are just occasionally confused for one another. So if we hadn't already evaluated the test set, we could go back and modify our input and then take funky functions and then try to separate them or even change the model. So if you want to go back and then change the model and change some of the input and augment some of the features in order to improve or see what the effects on the confusion matrix are, feel free. These are relatively lightweight models, so they're easy to change and modify. So more specifically, so we had a classification problem just now, which was just classifying into one of 3 classes. There's a lot of, not a lot of dictionaries, a lot of nomenclature, a lot of vocabulary. There's a lot of vocabulary which comes out of binary classification. So in a lot of contexts, what the more complicated multi-class classifiers are doing is something on top of binary classification. So one of the things that you might hear a lot is one versus rest, which is you take one class and then you try to see if you can identify that class versus any of the other classes, so the rest of the classes. So because so much of classification is based on binary classification, it's important to look at more detail. So in medical context, which is probably the one which is going to be of more interest for us, it's questions like, is the patient sick? Do they have this disease? Yes or no? Does this MRI have evidence of tumor? Yes, no. And then more specifically, if you're looking at sections of an MRI, does this section have evidence of a tumor? So there's a lot of vocabulary for this. And just so that we're on the same page, we're going to briefly go over it. So the positive and negatives, binary classifiers is just 0s and 1s. So you have either the negative class 0 or the positive class 1. You can flip the names if you want to, but that is the convention. So a true positive versus a true negative. So the true part of that refers to the correctness of the prediction. So if your model says 1 and the true value is 1, that is a true positive. A false positive and false negative, so false refers to the incorrectness of the prediction. So a false positive means that the model predicted class 1, but the true label was class 0. Now, so the metric that we just saw, that we were saying was not entirely always informative, is accuracy, which is the ratio between the correct predictions and all predictions. So it reflects the fraction of correct predictions, or how often is our model correct. There's also sensitivity, which is the ratio of true positives and all positive labels. So true positive over true positive and false negatives. So these are all the ones that have a label value of 1. So our sensitivity reflects a model's ability to detect a positive case. It answers the question, if the patient is sick, how well do we predict it? For specificity, it's similar, but for negatives. So it's the ratio between true negatives and all negative labels. And it reflects the model's ability to detect a negative case. So if the patient is healthy, how well do we predict it? So instead of asking if the patient is sick, we ask if the patient is healthy. How do we predict that? And then precision, which is the ratio between true positives and all predicted positives. So this reflects how often a model is correct and when it makes a positive prediction. It answers the question, if the model predicts a patient is sick, what are the chances the patient is actually sick? Okay. So feel free to refer to these definitions. There's also a very long Wikipedia article with like 100 different metrics, which are all interconnected between true positives and true negatives and so on. But these are the ones that we'll be looking at. So as as the model is trained, all of these metrics are going to initially increase because our model is improving. So as it makes better predictions, it's going to have a higher proportion of true positives and true negatives. So after seeing enough data, there's usually a trade-off between sensitivity and specificity. So after a point, if you say, if you increase the model's affinity for making positive predictions, so what that means is if your model is more likely to err on the side of, oh, well, we'll predict the positive case just in case, versus predicting a negative one, then the sensitivity is going to increase. If you predicted 1 for all cases, you'd have amazing sensitivity, but accuracy and specificity would be very low. And then similarly for negative predictions and specificity. So here, if we run this cell, we're going to use make blobs, which just creates 2 patches of points. Then here we're plotting the different classes in different colors. So we're going to look at what this code is doing in a second. But this is just to get you an idea, just to give you a sense of what the data we're dealing with looks like. So we've got some distribution of points, and they're both centered on, they're centered on different points. So here in the definition, we said, I want the first blob to be centered at 0, 1. So 0, 1. So the blue blob is centered around here. And then there's a bunch of points that are sampled around that. Then we said the second blob is going to be centered at 0, negative 1. So 0, negative 1. So ideally, the perfect separator well, perfect. The separator we might expect to be at 0. So we're actually going to evaluate that. So if we look at the if we look at this plot, we'll see that some of the data overlaps, but that it can be separated reasonably well with a simple horizontal line. So if we classify everything above the line as 0 and everything below the line as 1, we're basically just turning our horizontal line into a classifier. So in this exercise, we're going to vary the position of that horizontal line and then see what its effects are on the 3 metrics. So accuracy, sensitivity, and specificity. So this part is, so in machine learning, sensitivity and specificity are used a little less commonly. There they prefer things like precision and recall, but you can convert those directly to sensitivity and specificity. So that's what's been done here. You call this like you would any other function. So if you want the sensitivity, it's just sensitivity widespread. So here I just defined it so that you guys don't have to worry about it. So one of the things that is probably going to simplify your lives quite a bit is not related to machine learning. It's again related to Python, and it's something called logical indexing. So here, if we look at this plot, we can see that I use square brackets to indicate, okay, these are the indices that I want, but I didn't put in numbers, I just put in this equality, or this comparison rather. So this part, that's what's called logical indexing. So just to illustrate the point, we're going to generate some easy to recognize data. So we have X, which goes from 0 to 9, and then Y, which goes from 30 to 39. Then we're going to print those values to see what they are. So logical indexing in Python means that Python lets us use true and false values to select entries. So if you say that a certain entry, if you index the third entry with true, that means, yes, give me that one. If you index the fourth value with false, that means, no, don't give me that one. So here we're going to use logical indexing to get on X, and then we're saying, everywhere that X is greater than 4, give me those values. And then similarly, if we want to select based on a different variable. So here we're saying, give me all the values of X wherever Y is less than 33. And lastly, we can also assign values using that indexing. So X is, so here we're saying that for all values of X greater than 6, give them a value of 6. So now if we run this cell, we see our X values, our Y. These are the values in X which are greater than 4, and then we can quickly examine that's the case. And then here we see the values of X when Y is less than 33. So 33, so there are 3 values before Y is equal to 33. So there are 3 values that are less than 33, and then we see that the corresponding values in Y are 0, 1, 2. Then lastly, for the assignment, we did X, we assigned all values of X greater than 6 to be equal to 6. So initially we had it going from 0 to 9. Now it goes 0, 1, 2, 3, 4, 5, and then repeats with 6. Okay, so this line is just as a reminder of how we actually generated the data. And this section is the part that you should fill in. So I've already filled in part of it just to give you a hint of how to do it. And I'll give you a few minutes to fill that out. If there are any questions in the meantime, let us know.
Alex?
Yep.
Could you go over how you're defining Y prediction? I think that was one of the questions in the Slack.
Okay, so the question is, where is YPRED coming from in the definition of sensitivity and specificity? So where is YPRED and YTrue coming from? So YTrue, those are the labels that we're coming from, that we generated using our make blobs. The YPRED, that is going to be coming from a model that we're going to train. So the model that we're training in this case is just the horizontal line. So YPRED is basically just the predictions, or what we think the label should be on a certain sample. So in this plot, for example, we see that these are the labels which are in our ground truth, our data set. Now, as we move a horizontal line from down here, let's say, and then move it upwards, we're going to say that everything above -1 is blue. Now we're going to have some fraction of the points which are incorrect. So for example, the values, the red X's between -1 and 0, those are all misclassified. And then as we move higher and higher up and say, okay, well, all the points above 2 should be blue. Well, that's correct, but that's everything below that, or all the blue points below that line are going to be misclassified as red, and that's going to affect our accuracy, sensitivity, and specificity. Okay, so I'm going to walk through the solution. So we have two classes. So we want to predict all the classes above, all the points above a certain value, so P in this case, to be class 0. So here we have our YPRED, which is just properly shaped. So we start the indexing, and then we say X data. And since we're looking at the Y position, we take the second dimension to be 1. then we compare that to the value of p. So if the y position is greater than p, so now we're looking at all the samples in ypred where x data is greater than p. And we'll just assign that to 0. And then similarly for less than or equal to p, we'll assign that to 1. And then defining sensitivity, specificity, and accuracy. That's just a function call from the functions that we defined. So we define sensitivity, specificity, and accuracy score. Oops. And then once these are defined, we just want to append it to the list. And then we can plot. So if we run this, live coding worked. So now if we see this, so we have our two classes, which are our data, which is here, where we can see the two classes, blue and red, or X's and dots. And this is the behavior of sensitivity, specificity, and accuracy when we're moving that line up. So here we started at -1. So here, if we have the straight line going through -1 and we say everything above that is 0, well, we have very low sensitivity. Is that right? Yeah, so we're going to have a, no, it's not right. Oh yeah, sorry, sensitivity is for a class 1. Okay, this is fine. So we're going to have a very low sensitivity because we're classifying, we're not classifying all of the reds as reds. We're saying that a lot of these reds are blue. So then the accuracy overall is still not bad. So we're at 0.7 accuracy, which means that we're roughly correctly predicting 70% of our data set. Then as we move the line upwards, we see that the sensitivity increases to 1. So at the very top, when we say, okay, well, everything is class 1, then we're going to have a very high sensitivity because we detect all of the class 1 points. Now, if we look at the behavior of this, we see that the accuracy at the very left part of this is basically at its lowest point, and then it increases, it reaches some maximum, and then goes back down. So the question that you might be able to answer or figure out that it's a trap was, what is the best position for the dividing line? And in this case, it probably is 0. So according to this, we have maximum accuracy. We've got a good balance between sensitivity and specificity. So intuitively, that seems right. But the answer is still, it depends. So suppose that this problem wasn't just classifying blobs. Suppose that this was predicting whether a patient had cancer. Now, if your model is correct and you say, yes, that patient has cancer, when that patient has cancer, then you're golden. And then same thing if they're healthy. If you predict that they are healthy, then that's not a problem. The very important consequence comes from what happens if they don't have cancer and you say that they do. So that'll trigger a whole bunch of invasive tests and biopsies, and it's going to waste a lot of people's time. It's better to check, but it's still a cost which is associated with that error. But what's much worse in that context is a false negative, where a patient comes in and then who has cancer or has some tumor, and then your model says, no, you're healthy, go home. So depending on the context, you may want to have a model which is more sensitive, and yet you're okay being wrong about predicting positive cases, because the cost associated with errors isn't the same for false negatives versus false positives. So again, the answer to the question, what is the best position or what is the best value, depends a lot on the context. So the previous example, so were there any questions on that example before I move on? Okay, I see some activity in the Slack, but it seems to be mostly module errors or versioning errors. All right, so in the second example, we showed how the three metrics varied relative to one another. But the data that we generated isn't really typical of medical data. So one of the things that is kind of unusual is that there was a balanced data set. So what that means is that we had the same number of samples in class 0 as we did for class 1. So there wasn't that imbalance between the two. So if we examine the plot that we created, it's really hard to see why accuracy as a metric would make some people a little nervous and doubtful of your results, because qualitatively it peaks right where the other two intersect. So why wouldn't we use accuracy? So we're going to look at what happens to sensitivity and specificity when we don't have a balanced data set. So what happens when we have an unbalanced data set? So most of this is already defined for you. So here you can define the relative imbalance between the two. So the number of samples for class 0 versus the number of samples for class 1. So you can modify these parameters if you like. So I put in the code I had here. So if you want to have a more direct comparison, just put the code that you wrote here, and then it'll generate the plots. And then if we run this cell, this error is normal, don't worry about it. We see a plot which is a little different. So this is what our data actually looks like. So here we see that there's a lot more class 1s than there are class 0s. Now we see that the accuracy doesn't peak in quite the same spot. It doesn't peak where you have the intersect between the two. And the reason for that is that accuracy doesn't really care about the relative proportion of true negatives or between the proportion of the classes. It just cares about accurate results. And one of the, I used to work at a company, and one of the things that one of the bosses would say is it's really easy to predict Alzheimer's with high accuracy. The reason being that if you look at the entire population and you predicted that nobody has Alzheimer's, you'll get something like 98% accuracy right off the bat. But you're not really doing anything useful. Like, nobody's going to give you a medical degree or PhD for Alzheimer's prediction just because you can get 98% accuracy. So this is where the hesitation comes from with accuracy. Without knowing that the dataset is balanced, accuracy itself doesn't really mean anything. So now if we just go back up and then modify these to more extreme. So if instead of 500 and 100, if we did 10, well, here we have an accuracy bar, which basically maps sensitivity almost exactly, which is also bad. So the question of not having enough data isn't just getting more data points. So if you're trying to predict Alzheimer's, you don't want to just keep bringing in more healthy controls. That is not going to help your model. Your model has lots of that, lots of those samples. You also want you want some additional samples from the class that you're actually interested in. So now, check if there are questions. Can we go over logical indexing again? I'll do that at the end of the notebook. Okay, so the third example is we're going to look at something which few of you have probably heard of, which is the ROC curve and AUC, and what that actually means. So one of the questions based on the previous example you might be asking is that if the best model depends on the context, how can we compare models? Is it possible to compare models? And if we're proposing to use a model for a certain problem, we don't know whether other people would even agree with our selection. So, for example, in the previous example that I gave about false negatives and false positives, we might be okay having more false positives and false negatives. So we want to make sure that we detect everyone that has cancer, and we're okay being wrong about that, so long as we don't send anybody home while they do have cancer. But if you were to present those same results to the coalition of evil doctors, they're probably going to disagree with you. And I'm not saying we should cater to the coalition of evil doctors, but you understand the point. So there's a couple measures that help us work around the problem of where do you think the optimal set of parameters or the decision boundary should be? And the question instead boils down to, when the truth is X, how often does my model predict X? And then we balance between 0 and 1. So the simplest way is just to plot it and then discuss it. And the plot that we're going to generate is the receiver operating characteristic curve, or ROC curve. And it's the balance between sensitivity and the false positive rate, which is just 1 minus specificity. And we're going to look at what that plot means. And again, Sclern has a metric that just lets you plot the ROC curve directly. So if you have your estimator, you have your data, it'll plot the ROC curve for you. So the instructions for this example is just initialize the logistic regression classifier, which should be, well, which is right here. We create 2 data blobs, balanced or not is fine. And then we're going to visualize them. That's just to see what it is that it's doing. So here we see that the blobs are separate and they're off center. A straight horizontal line is not going to cut it. Slanted one would, but this is fine. Then we're going to train our classifier to separate these 2 classes. And then we're going to plot the ROC curve. Oops. So now the question is, what does this curve tell you? And from that, could we determine what the best classifier should be? Okay, so for the first question, what does the curve tell you? Well, it tells us that if we are willing to accept a 0.2 false positive rate, that we can expect a true positive rate of oof. If you squint really high, if you squint a bunch, it'll look like 0.95 or something. So what this does is it lets people pick what they're willing to put up with. So for example, if we really want a very low false positive rate, then you might say, okay, well, I'm going to select whichever set of parameters allows 0.05 false positive rate. Then you go up here and then it would tell you, given that false positive rate, you can expect a little over 0.8 true positive rate. So this is basically a summary of the trade-off between sensitivity and specificity. So it's basically just kicking the question of what is the best classifier down to whoever is looking at the curve. Now, the way that we can summarize that curve in just one number is AUC, which is the area under the curve. And it's basically just the integral of this curve. So if you have the absolute perfect prediction, which is you never have anything wrong, it's going to look like just this, what's it called? Just a square corner, so a right angle at this part, and then go here. If ever you see that, be very suspicious. That basically never happens. And anything which is above the diagonal line is considered to be an improvement over chance. Okay, so we're going to take a few minutes for questions, and then we're going to move on to the last section, which is going to be relatively brief. So if you have any questions, clarifications, or you'd like me to go over something again, let me know in the Q&A, and then we'll address the question. So the first question is, can you talk about how ROC curve works under the hood? So we kind of saw how it worked under the hood in the previous example. So it's basically just changing the threshold for deciding whether it's class 0 or class 1. So yeah, up here. So in the first example, what we did is that we moved the bar upwards and then used that as a threshold between one class or the other. And then we saw what its effect on these two plots were. So if you wanted to, you can actually plot the ROC curve based on sensitivity and specificity here. You'll have to take one minus specificity, but all the information for the ROC curve is stuff that we did generate. And then the follow-up question is how the area is calculated. You would just take a normal integral across all the, so these are all sample points. So you would just take the sum. Okay, there's another question. How can you find the corresponding threshold horizontal line from the ROC and AUC? I don't know. Imagine that wouldn't be under the plot, probably just be under the ROC curve, which I did not import. All right. So if you look at so instead of plot ROC, if you just looked at the ROC, that provides with, and that'll provide you with all the information that you're looking for that's coming in from the background. The plot ROC is just a helper function because most people are just looking to plot it. So if you're looking for the individual thresholds, then you would look at the return value from ROC curve. Do people ever run stats on AUC being above 0.5 to make claims of the model being significantly above chance? Yeah, I kind of regret making that claim. So I'm not entirely sure if you could actually do stats on this. I think, Jerome, you might be able to answer this better than I could.
I would say if you need to actually do a statistical test to check if the model is better than chance, then it's not very good anyway.
Yeah. Well, yeah, okay, that's true.
But as you said before, Alex, you could also do permutation tests for this and look at the variance of the AUC you get with random data.
So there's a question about logical indexing, specifically about how it was used in the context of example 1 to set the predictions. Okay, so in the context of example 1, what we were doing is that we were, scroll up a bit, where's the plot? So we were given this data and we were moving the threshold of one class or the other up. So here, when we were doing this logical indexing, what we're saying is that take all the indexes for the samples, so Y-pred, that are above a certain threshold, the threshold here being P, and then give them the value of 0. And then in the following one, in the following line is take all the ones that are below that line and then assign it to class 1. One more question to rephrase my previous question. Would it make sense to create 2 machine learning models that take the same data, one model having excellent sensitivity and one model having excellent specificity? So intuitively, no, but I don't have a good explanation as to why. I think it's mostly because if you're trying to, so here if we look at our inbounds data set, for example, I think it'll be a bit clearer in there. So here if we just put this something a little less silly. So if you train a model to have excellent sensitivity, you're just sacrificing a lot of your specificity in order to get that. And then if you had the opposite, where you have a model with high specificity, then you're sacrificing. So they're both working, they're kind of both working on the same data set, so you're not really going to have much information. So what you could do is have something like an ensemble method, where you combine the prediction of multiple similar models and then put another model on top of those predictions in order to make informed decisions. So there's something called the weak classifier, which basically just does a terrible job at doing everything. But if you have a lot of weak classifiers and you put them together, you can end up with a semi-decent classification. But we basically don't really have time to look at ensemble methods. Okay. There's one more question, which is, how do you know which model to use if one model says, yes, the patient has Alzheimer's versus another one that says, no, they don't? Well, it's the same way that if you went to 2 different doctors and then one said, oh, okay, apparently there's an answer to something. Okay, never mind. Well, I asked the question. So the the answer is kind of the same to if you went to two doctors and then one said, yes, the patient has Alzheimer's versus no. It'll depend on which model is known to be better. So, for example, which one is more accurate, which one is more sensitive, which one has higher specificity, which one has better recall, and all these other metrics. Also, if you have enough models where there's some uncertainty, the question isn't always go get a better model. Sometimes it's go get more data. So normally in a medical context, you'll have some early screening where those are meant to be extra sensitive. So for example, a very simple blood test, which is going to be more sensitive than specific, which means that you're going to take in more patients that are healthy than you otherwise would. And then further tests, which are a lot more accurate generally and a lot more sensitive and specific, are then going to be done. And those additional tests are the additional data which is being acquired. Okay. So that covers the difference between regression and classification, along with a couple metrics on related to binary classification. Now we can go to the last section, which is section 2.3. And this one's going to be relatively brief. So one of the things that Yarkoni mentioned in his talk on Wednesday was supervised versus unsupervised learning. And so far, we've seen a whole bunch of data where all of that data had some label associated with it. So in the previous example that we were just looking at, for example, was the classification of the two blobs. So there we knew which blob belonged to which class because we generated it and then we were able to see, well, okay, that blob is class 1, that blob is class 0. But what about data sets that don't actually have those labels? So if we run this first cell, if I asked most of you to classify one way or another, so if I gave you some point in there and I told you to just tell me, is it one class or is it another class? You'd be able to take a look at this and then say, okay, well, all these clumps of points probably are the same class because they're all next to each other. And then down here, you'd say, well, this is a separate class. Then you can run this a whole bunch of different times and then you'll see that, well, no, there's actually 3 blobs, but it's not always obvious. But intuitively, you can make a half-decent guess as to what belongs to what. And we're not training our brains, it's just that we can see that this is obvious. So how can we do this using machine learning? So that type of algorithm is a class of algorithms called clustering. And the idea is that if you have a set of data or clump of data, which looks more similar to each other than everything else, then they probably belong to each other. They belong to the same class. So the way that the algorithms works, that they look at the data, identify which points are most similar, and then apply labels when they apply the same labels to data when they're similar enough. Then the definition of similarity changes across algorithms. So one of the simpler ones is k-means. And all that does is that it initializes a couple center points and then looks how to best classify the clumps. So here, for example, I would say, okay, well, all of these look similar to one another. So if I classify these as all being the same, it's going to minimize my internal metric of similarity. So k-means does have a couple different limitations, but for our purposes, it'll work just fine. So for this exercise, we're going to do something very similar to what we did before. We're going to generate data using make blobs. We can store ylabel, but we're not really going to use it. Then we'll want to plot the data to see what it looks like. Then we're going to initialize k-means, and then we're going to initialize it with a certain number of clusters. The exact number of clusters I'll leave to you. Then we fit our k-means data to our k-means object to our data. And note that since this is unsupervised, we don't fit the labels like we did before. So it's not, here is our data, here are our labels. It's really just, here's our data, fit this. And then lastly, we're going to plot the predicted labels. So what our k-means estimator guesses the labels are. And then we're going to compare the plot between what we clustered together and then what we actually generated. Okay, so I'll give you a few minutes for that. Okay, so I'm seeing the time go by and I really want to get to the next example because I think it's going to be of more interest to people. Yeah, so here's a solution. We just initialize with some number of clusters. We fit our data. We get our predictions from our model, and then we plot using logical indexing. So I suspect that what a lot of people might have been hung up with is the plots. Mostly because the logical indexing is a little tricky and it's not quite as intuitive if you're not used to it. But everything before that is all stuff that we've seen before. So we had some estimator type object where we're initializing, we're fitting, we're predicting. So in terms of how to use these things, it's very similar to what we've seen before. So now we can look at our plots and then at our blobs and then see that so these are our predicted clusters. So we can see that it actually looks like it does not a bad job. So this data seems most similar to the blob next to it. And then we have two separate blobs over here. Now, one of the parameters that we had to initialize k-means with was the number of clusters. So what happens when you have a different number of clusters? So if instead we'd said, oh, well, I think we actually have 5 clusters in here. Well, then you end up with some funky results where, yeah, you'll get one cluster, which is fine, but then one cluster here, which seems to be divided into 2 different ones, and then similarly down here. And if you don't have a way of verifying these results, that's kind of problematic because what is good depends mostly on knowing what the answer is. And then if we were to instead move the blobs closer to each other, so just to make sure that, just to see if it would overlap, what we would eventually see is that the division becomes more worse and worse. So it becomes a lot harder to distinguish one blob from the other. And because if we look at it visually, we can't distinguish it, then k-means is not really going to do a much better job than that. So there's a question about initializing the centroid, and Yes, and so Sclearn does that automatically in the background. If you have some extra information about where you expect the centers to be, then yes, they can be initialized. There's a parameter in k-means for that. So now the next example I want to cover is something else which is unsupervised, but is not often considered as machine learning by a lot of people, the same way that, so I'll often ask if people have done any kind of machine learning, and then the answer will be, oh, no, I haven't, I'm new to it, etc. And then I'll ask them if they've ever done linear regression, and they'll say, oh, yes, of course I've done that. And PCA kind of falls in that same category where, yeah, you can treat it like machine learning, but a lot of people don't conceptually. So what PCA is okay, so what it actually is this, which is probably going to be meaningless if you're not sure what a covariance matrix is or what eigenvectors are. But more intuitively, what PCA does is it transforms your data, and then instead of looking at X, Y, Z coordinates, it realigns the X, Y, Z so that it accounts for the most variance in your data. So there we don't care about which way where the data is located. We care about where it's varying the most. So for example, if you had some diagonal line with a whole bunch of points spread across it, you're going to have mostly variance being along that line. So as we saw with clustering, PCA is unsupervised, and it doesn't look at the data labels when it's computing the best principal components. So one of the common uses of PCA is to do feature space reduction. So a lot of the time you'll have a lot of features, depending on if you're in imaging, for example, some of the images you're going to get are going to be millions of voxels. And you may not want to have millions of features. So instead, what we can do is get the principal component decomposition, where instead of looking at all million voxels, we just look at the ones at the way that the images vary the most. So we don't really need to consider noise that is outside the head in an MRI, for example, because that's going to be much lower variance than the signal that's coming from inside the head. So in the example that we're going to see here is that we're going to reduce data from 4 dimensions to 2. And not only is that going to help us visualize it, but it might actually make it easier to fit. So the iris data set that we saw previously that we couldn't really plot super well because it had 4 features, and it had 4 dimensions. But if we don't really care about what our features are, we can find some combination of sepal width, height, petal width, and petal height, or length, that better defines the variance that we see in our data set. So for example, if we have sepal width and height combined to one feature instead of 2 separate features, and we can still account for most of the variance in our data set, then we can simplify our data without sacrificing the information content. So that's what we're going to do here. So we're going to use PCA to reduce the number of features from 4 to 2. And then we're going to plot the features. So as we did before, we're going to load our data set. We're going to initialize our object. We're going to apply the transformation. So previously we'd seen predict. Here we're going to use transform or fit transform. There's a description slightly lower down here. And And then that's going to put our 4-dimensional feature space into 2 dimensions. Then we're going to transform our dataset into PCA components, and we're going to plot them. And then we're going to visually separate them just to be able to see what's going on. And then we're going to fit a logistic regression classifier. Now, one thing that's important to compare is if you have the full data set, you're almost guaranteed to have more information because you have more data. But it's not always the case. So we could actually account for 98% of the variance, and that could still help us divide our data very cleanly. So one of the things that we're going to compare is how does one model, which is fit on our full data, compare to our model that we're fitting to transform data. So there's instructions throughout the cells just to help you along. And if there are any questions, we'll monitor those also. Okay. So I'm just copy paste the solution. So here, if we have our data set here, we initialize our PCA object using 2 components because we only want to retain 2 components. Here we transform our data into the principal component space, and the way that we do that is fit transform. And then using this data, we'll use logical indexing again to plot the different classes into different colors. So previously we could only get a glimpse into 2 dimensions, and it was very hard to tell apart the clusters and get an intuitive feel for it. Here in 2 dimensions, we can see that, okay, there's one cluster which is very far from the other 2, and that one is going to be easy to separate. Then we see that the last 2, or the second 2 classes, where there's a bit of overlap between the 2. So we can see that, so previously what we had was there was some confusion between 2 classes. And just eyeballing it, it's not too surprising that there was that kind of error, because you can see like there's a data point here, which personally I would have clumped in with this class. Now we just visualize a 4D data set into 2D. Now one of the difficulties with going from higher dimensions to lower dimensions is that this might not be very well separated in 2 dimensions, but it could have been in 4 dimensions. So the question is, have we reduced some of our predictive power by removing those 2 dimensions? And the answer, just like everything in machine learning, is, well, we can just do it and see. Copy this. So as we did before, is that we're going to have some logistic regression. We're going to fit on our PCA features and then try to predict the labels. So this is just the fitting operation. When we want to actually evaluate our data, we won't be able to. We can use the same PC that we did from before, where we just transform that, and then we can generate the score. And then the second step is, okay, well, what if we use the full non-PCA dataset? How does the performance compare there? So if we just run this cell, so we see that the PCA feature score, so the score with the PCA features is 0.8, the full feature score is 0.85. Now, if you were to run this with different subsets, you'll end up with different but comparable features. And the answer is basically you don't lose much information. So there'll be some splits where the PCA feature does slightly better than the full feature. But on the whole, they're pretty comparable and we haven't lost much information. Okay, so that's it for today's content. I'll have the exercises up early this afternoon. If there are any questions, we'll stay on the call for a bit.